Hello students, welcome to this video. Now in this video we are going to look at fluid dynamics. Okay, so we have various questions under fluid dynamics, but I'm just going to begin with I think this first example, and then the rest are going to follow. Okay, so with me here, I would like to explain on the rate of flow of a fluid. Okay, so I have drawn this particular system. We assume that it is a pipe which has a larger surface area on one end and a smaller area on the other end. Okay, so there's a difference in the radius between the two ends. So now assume a fluid is flowing from the left. The amount of volume that passes the cross-sectional area of this particular tube is known as the volume flow rate. Okay, the volume flow rate. So this is a volume of the fluid that passes through an area, or rather a section of the tube at a given time t. Okay, so the volume flow rate can be given as dv dt, which is equal to the area through which the fluid is passing multiplied by the speed of that fluid. Okay, so this is the volume flow rate. Now suppose we want to consider both ends of this tube. We have point A here with surface area A1, okay, A1, and the fluid moving at a speed of V1. Okay, then point 2 here we have surface area A2 and the fluid moving at a speed of V2. Okay, so if the fluid is incompressible, then we are saying that the volume flow rate at point 1 is equal to the volume flow rate at point 2. Okay, so for instance, if we are saying the volume flow rate at point 1 is given as area at point 1 multiplied by the speed of the fluid at point 1, then the volume flow rate at point 2 is going to be given as the area of this pipe at point 2 multiplied by the speed of the fluid as it passes through point 2. Okay, so this equation is known as the continuity equation for a fluid which is incompressible. Okay, so now it's easy here to determine the flow rate at any of the 2 points. So long as you're given the initial speed of this fluid from any particular point, you can also determine the other speed on the other end of the tube. Okay, so incompressible. So this is for incompressible fluids. Now if the fluid is compressible, okay, if the fluid is compressible, we are simply saying that the density is not the same at all points through the tube. It means there's a variation of the density or the mass as the fluid is passing through the tube. So the continuity equation therefore changes, and we have now the mass flow rate. Okay, if the fluid is compressible, we are going to have the mass flow rate, which is the mass that is passing across a section of the tube at that particular time. So now the mass flow rate is given by simply multiplying the density with the volume flow rate. Okay, so if we are doing this, then the continuity equation for the mass flow rate changes. We are going to have at point 1, we'll have the density of the fluid as it enters point 1 multiplied by the area at that point multiplied by its speed, and this must equal to the density at point 2, because we are saying the density is not consistent throughout the flow, times the area at that particular point multiplied by the speed of the fluid at that particular point. So this is the mass flow rate, and the form of the continuity equation has changed to this. Okay, so therefore this is for compressible fluids. Okay, so there's another situation that we need to consider. We are given a fluid of which we assume has no viscosity. Viscosity, just the internal friction of the fluid. If we assume so, and we would like to determine the speed of this particular fluid at any point, so let me just redraw that. So something like this. Okay, something like that. So we have the area and another area there. So now, if a system is assumed to have no internal friction and it is also incompressible, rather the fluid, if the fluid is said to have no viscosity and is also incompressible, then for that particular problem we are going to use the Bernoulli's equation. Okay, so Bernoulli's equation is given as if the fluid is moving, then Bernoulli's equation is given as the pressure at point 1. Let's assume this is our point 1. The left end is point 1, and the right end of this tube is point 2. So the pressure at point 1 plus the pressure, which seems to be like the gauge pressure, times height 1 plus half rho, which is the density, times the speed at point 1 squared, is equal to P2 okay, so this is Bernoulli's equation. All right, this means that the fluid is actually flowing, or it is moving. If the fluid is not moving, then we have this coming out of the equation. It means that V1 is equal to V2, and they are both 0. And then we have a more simplified version of this Bernoulli's equation. So because we are dealing with fluids that are moving, we need these expressions that have the speed. So this Bernoulli's equation is actually derived based on the energy, okay, of that particular fluid. All right, so now the heights, okay, we have P1 plus rho GH1, and also on the other side we have an H2. So if the system is horizontal, then we are going to look at the center of this particular system. So, and we are going to make that as the reference. So if this is the center on this other end, then the other side is going to be right there. So we measure this distance from the ground like that, and we are going to discover that they are actually equal. Okay, if a system is horizontal, then we are saying that h1 is equal to h2, and if this is the case, then we are going to see this and that disappearing in the equation, and the equation becomes more simplified, and we'll have p1 plus 1 over 2 rho v1 squared equals p2 plus 1 over 2 rho v2 squared. Okay, so this one becomes our Bernoulli's equation. So if the system is vertical, we are going to discover that the heights are actually different, because for instance, if you have a system like this, okay, a system like this, that is your center, that is your center. So the height of this with relative to the ground is actually different from the height of that other end, okay, implying that h2, or rather h1, will not be equal to h2. And if that is the case, then Bernoulli's equation remains the way it is. Okay, so now we are dealing with a horizontal system in this particular tutorial sheet, and if that is the case, then let us go ahead and look at an example of a question that involves a system such as this one. Right, so we have this tube, which may be used as a flow meter, right? So this thing is used at a service station, and the flow rate of gasoline through a hose having an outlet radius of 1.2 centimeters. So the density of the gasoline is given, and now they are saying that if the difference in pressure is measured to be 1.2 kilopascals and the radius of the outlet, rather inlet tube to the meter is 2.4 centimeters. They want us to find the speed of the gasoline as it leaves the hose. Okay, they want us to find the speed of the gasoline as it leaves from this end. Okay, so it's entering from there and then goes out from that side. So now they want us to find the speed as it leaves this particular tube on the other end, on the outlet, so to say. So it can be very prompting here to actually think of the continuity equation. Someone might assume perhaps I can simply say A1 V1 equals A2 V2. So you cannot use this particular equation for a very simple reason. We do not know the initial speed of this fluid as it enters the tube from the inlet. Therefore, we can't determine also the speed of the fluid as it leaves the outlet. Okay, it means we are going to have two unknowns in this expression, so we shall not use this. For this case, we are going to use the Bernoulli's equation. All right, we are going to use the Bernoulli's equation and find an expression for the speed at point 2 here. All right, so let us go ahead and just rewrite that equation. So Bernoulli's equation, as we have derived it initially, we are saying it's going to be P1 for a horizontal system. It's going to be P1 plus half rho V1 squared, which is equal to P2 plus half rho V2 squared. Okay, This is Bernoulli's equation for a system that is horizontal, because we can see that this tube is actually horizontal, meaning that H1 and H2 are equal, and therefore they are out of the equation. So now they go further to tell us that the pressure difference P1 minus P2. So if we do that, we are going to have P1 minus P2 equals, okay, we're going to take this guy to the right side because we have taken P2 to the left. Therefore, we will have 1/2 rho, since the density is the same throughout the fluid, and then we're going to have V2 squared minus V1 squared. Okay, so what we want to find here is actually V2, okay, the speed at point 2. Okay, we want to find this guy because that is the speed at which the fluid is actually flowing out of this tube. Okay, so what we have is actually P1 minus P2 being equal to 1/2 rho multiplied by V2 squared minus V1 squared. Okay, so again, when you look at this, we still have two unknowns. We don't know what V1 is, we don't know what V2 is. Okay, so from here we can consider the continuity equation for an incompressible fluid, because that is what we are looking at, and we know that it's given as area 1 multiplied by speed 1 equals area 2 multiplied by speed 2. Right, so we want to find speed 2. So if we make V1 here the subject, we'll have V1 equals area 2 V2 over area 1. Okay, so we are going to use this guy, okay, and substitute V1 in our expression here. Okay, I hope you're following. So if we do that, we are going to have that P1 minus P2 equals 1/2 density multiplied by the V2. We have V2, okay, let me write that properly. Okay, V2 squared minus the expression that we just obtained for V1. Let me just put these brackets. Okay, so the expression that we just obtained for V1 was A2 V2 over A1 squared. Okay, I hope it is making sense now. You can see from here that the only thing we are remaining with as the unknown is actually V2, okay, because we can find the area given the diameters. We can find the areas for both ends of this tube. The density of the fluid is also given, and the pressure difference here, P1 minus P2, is also given. So it's just a matter of now finding an expression for V2 in the equation. All right, so let's work around that and see what we get. Okay, so with this, what we have is going to be, this is going to be, okay, so let's just assume this guy is always on our left. We will just be carrying him along. So now we say this is going to be half rho multiplied by V2 squared minus A2 squared V2 squared over A1 squared. Okay, So we work around that. We are going to have rho over 2 multiplied by, so we have A1 there. So I'm going to take you through every step. So that is A1. Then on top here, we do that basic mathematics. We are going to have A1 squared, okay, V2 squared minus A2 squared V2 squared. All right. Okay, hope you're following. And then we move on. We are going to remain with P1 minus P2 being equal to rho over 2 multiplied by V2 squared times A1 squared minus A2 squared. Okay, let me just use brackets here. All right, over over of A1 squared. Okay, so from here now we can easily find an expression for V2. We are going to have 2 A1 squared multiplied by P1 minus P2 is equal to V2 squared multiplied by A1 squared minus A2 squared, from which we are able to obtain V2 as the square root. Okay, V2 will be the square root of 2 A1 squared multiplied by P1 minus P2 over rho multiplied by A1 squared minus A2 squared. Okay, so I think now you can see that life has become easier. Okay, we simply find first the areas. Now the pressure difference is already given, remember. I think that is 1.2 kilopascals. All right, so from here we simply obtain the areas of each side of that tube and simply substitute here. Make sure the values of these areas are in standard units of square meters. Also the pressure here that is given in kilopascals, kindly take it to pascals first. Okay, simply multiply by 1000. And the density that you're given, I think it's already in standard units, so that should give you the velocity or rather the speed of the speed of this fluid as it leaves the tube through the outlet. Okay,